Today we're taking a look at section 3.1, which is quadratic functions and inequalities. We're going to take a look at a couple of different ways that we can see quadratic functions written. And of course we've seen some quadratics before. We've seen particularly the quadratic equation. We've seen parabolas, those kinds of things, and we're going to look more specifically at those in this chapter. So the first form that we're going to take a look at is called the general form. And the general form of a quadratic equation looks like this. Y equals ax squared plus bx plus c. And sort of the one condition here is that the a cannot be 0. If it were 0, obviously there would be no x squared term and we'd have something linear. So we can't have a being 0. That leaves a having two options. Either a is positive, and if it is, then we have a parabola that opens up, right, a U shape. Or a is negative, in which case we have a quadratic or a parabola opening downward, and it looks like that. The vertex is the point on the parabola that is either the maximum if it opens downward or the minimum if it opens upward. And the vertex is actually found by taking the coefficients in front of the linear and the quadratic terms and making a ratio with them. In particular, x is equal to b over, or negative b over 2a. And then you can find the corresponding y value by simply plugging that x value back into your function. The axis of symmetry is this sort of line that cuts the parabola into equal halves. It's a symmetric graph, of course, along that line. And that line is found at the vertex's x value, so it's x equals negative b over 2a. And please, please, please remember the x equals part. If you just tell me that it's the negative b over 2a value, that's a value. That's not a line, which is what we have for an axis of symmetry. So the first thing that we're going to do is we're going to take a look at a couple of examples where we find some of these pieces of information. So our first example, f of x equals negative 2x squared minus 8x plus 9, and we're asked to find the vertex. So the vertex formula says that x equals negative b over 2a. And the b value here is negative 8. So this is the opposite of negative 8, or positive 8, over 2 times a, and the a value here, which is listed first in front of the x squared, is negative 2. So we have 8 over negative 4, or negative 2. That's just the x value, of course, right? It says x equals. And we need to find the y value. And the way that we find the y value, as I mentioned before, is by plugging it into the equation. So we have this equation that's negative 2x, and our x is negative 2 squared, minus 8x, which is negative 2, and then plus 9. So you're welcome at that point to grab a calculator to simplify it, or just to work through the pieces, of course, on your own. And if you do, you'll end up finding that this is equal to negative 1. And the last step for finding the vertex is making sure that we actually write it as an ordered pair. It is a point, it is an ordered pair, so we're going to write it that way. So it's negative 2, comma negative 1 in a ordered pair notation. All right, we're going to try another one. Number 2, we're going to actually do a whole lot of parts. Take a look just real quick over here. All of these parts, we're going to go through H for this example. So y is equal to negative x squared plus 2x minus 6. The first thing it asks us to find is the axis of symmetry. Now, honestly, finding the axis of symmetry of the vertex first is almost the same step because both of them involve finding the same piece of information, and the x equals negative b over 2a. So we've got x equals, we have negative b, in this case my b value is 2, over 2 times a, and the a value is negative 1. So this is really just negative 2 over negative 2, or 1. So my axis of symmetry is x equal 1. And then also my vertex's x value is 1. We just need to find the y value, and the y value is found by plugging in the x value. So the x value would be negative, and then we've got, 1 squared, and then plus 2 times 1, and then minus the 6. So this is negative 1 plus 2, which would be 1, and then 1 minus 6 would be negative 5. So the y value of the vertex would be negative 5. So that's my vertex. All right, the next pieces of information, notice I've just copied the equation back onto this slide so we don't have to keep flipping back and forth, are the x and the y-intercepts, of course in the opposite order, y-intercept first. The thing to keep in mind here, and we've encountered this before, but it's been just a little bit since we've actually specifically talked about it, is that y-intercepts are the places when x equals 0, and then the x-intercepts are the places when y equals 0. So if we're wanting to find these, you're substituting in 0. You just need to make sure you're substituting into the right variable for the right component. So the y-intercept, letting x equals 0, is the easiest one, right? Because this would be y equals, and it would be negative 0 squared minus 2 times 0 minus 6. And you probably could have just looked at me and told me that to begin with. That's negative 6. So the x value is 0, and the y value is negative 6. So this is my y-intercept. For my x-intercept, there's more work to be done. And the reason there's more work to be done is because we have a 0 on the left, and then we have negative x squared plus 2x minus 6 on the right. And the problem, if you will, with that is that it doesn't factor. I can know that it doesn't factor pretty quickly because the factors of 6 are either 1 and 6, neither of which make 2, or 2 and 3, which don't combine in any way to make 2. So we're going to have to use some other method. You can use completing the square, you can use quadratic formula, whichever you prefer. And quadratic formula, I think, is probably just our most natural choice here, so I'm going to go with that one. Let me move this over here so we have a little bit more space. So this is x equals, it's negative b, and the b value was 2, plus or minus the square root of b squared, which is 2 squared, minus 4. The a value is negative 1, and the c value is negative 6. All over 2 times a, which is negative 1. So we have negative 2, plus or minus, and if we simplify underneath that radical, we're going to get a 4 minus 24, and 4 minus 24 would be negative 20. And if you're thinking about this, we've seen this happen, of course, before back in chapter, well, it was actually in the section P.7, back in chapter P. And you have a negative underneath the radical, which means you have an imaginary value. And we're working in the real number line, on the real number plane and everything right now. So for the purposes of what we're doing, this piece right here means that I don't have any actual x-intercepts. So there are no real x-intercepts because I ended up with a I, and the problem is essentially what's going on there. How does this open? Well, the direction that it's opened is depending upon what the a value is at the very beginning, and it's a negative 1, and so since it's negative, this will open down. And we're going to graph it. Okay, so what pieces of information do we graph? Well, actually everything that we have found so far. So we've got the axis of symmetry, that's at x equal to 1. So over here at x equal 1, we will plot a 1, and we're going to just make a dotted line straight down through that. Something like that will work. The second piece of information is the vertex. It's at 1, negative 5. So I've already got the line of symmetry, or the axis of symmetry. It's going to be along that axis. And then I had negative 5 on there. So this is 1, 2, 3, 4, 5. And we will put a dot right here. I don't have any x-intercepts. I did have y-intercepts. The y-intercept was at 0, negative 6. So that would be over here. So there's that one plotted. And then it's supposed to open downward. So opening downward would look like this. Remember, the vertex is my peak of my graph on this one since it's opening downward. So we've got this symmetric graph around this dotted line, and we have this going on. Our graph is increasing, basically on the left-hand side of this. So over here, the graph is increasing. So that would be from negative infinity to 1. And then it's decreasing after that from 1 to infinity. The domain is all x values. You can think of that from the graph. You can think of that from the equation. There are no x values that I have any trouble using or entering. There may be ones I'm not wanting to enter, but I can do it. So our domain is negative infinity to infinity. Our range is probably easiest to be found by looking at the graph itself. The graph's y values go down forever, right? But they never get any higher on the graph than negative 5. So my range values actually go from negative infinity to negative 5. And they do approach and actually include 5, so we will do the bracket on the 5. All right, so the next thing we're going to do is we're going to look at the other form of a quadratic equation, or quadratic function. This is called standard form. So the first one is called general form. It's ax squared plus bx plus c, right, like this one. And then this is standard form, and standard form looks like this. Y equals, you have your a value, and then it's x minus h, quantity squared, plus k. You might recognize this from a variety of things. Maybe you've worked with parabolas before. Maybe you recognize this because it looks kind of like the transformations we did back in Chapter 2. Hopefully that does ring a bell as a very recent exposure to this. Maybe you recognize this because it kind of looks a little bit like when we worked with circles as well back in Chapter P. So all of those things are true. There's some definite benefits to having the equation written in this form. Just to go through a few of the pieces of information. The a value at the beginning, still, if a is greater than 0, it opens up. If a is less than 0, it opens down, so that didn't change. The vertex is hk. Now notice that in the equation this says negative h, right? So it's the opposite sign on the x value. And then the k is the same sign. So that's actually really nice. Back over here, in order to find the vertex, we had to go through a little bit of work, right? We had to do negative b over 2a, find that value, and then plug it back in for y. But over here, we just have to sort of observe. If it's already in this form, it's readily available. Same thing for the axis of symmetry. It's x equals the h value that's in the formula too. So those are some really nice features about this particular form. Now, unfortunately, it's not always in that form. And so I'm going to talk to you next about how you're going about getting that in that form. And the key to doing this is to complete the square. All right, so if you'll remember, completing the square is a process we've done before. We did it with circles. We did it for solving quadratic equations. And we're going to work with them on quadratic equations here again. And so let me show you how we're going to them, because there is a little bit of a difference in what we're doing here as opposed to what we did before. The first thing you're going to do is you're going to pull our x terms at the beginning into a set of parentheses with a little space after the 6x. And then we have our plus 10 after the parentheses. The space right here is where I'll put the completing the square term. So how do I do completing the square? Well, it's negative b divided by 2. Almost like the vertex formula, right? Negative b divided by 2. Well, here's b, it's 6. So if I took the opposite of negative 6, it would be positive 6. And then 6 divided by 2 would be 3. And then the last step is that I square it. So 3 squared would be 9. So again, the way that I did that is I did negative 6. We'll go ahead and make that be a 6 now. Negative 6. Sorry, the opposite of negative 6. Let me do this again. Let me rewrite. Actually, it doesn't make any difference because we're going to square it. So let me just do that. So negative 6 divided by 2, and then we have it squared. So that'll work. That gives me 3 squared is 9. Now, I can't just go adding 9 to one side of the equation. That obviously doesn't just, we can't do that. It would change the value of the equation. Now, what we had done before when we did circles is if we added 9 to one side of the equation, we had to add 9 to the other side of the equation. And we could do that here. It wouldn't hurt anything, but it would kind of make things one step longer. Instead of adding 9 to the right and to the left, we're going to add 9 to the right and subtract 9 to the right. So our compensation is on the same side of the equation instead of being on either side of the equation. Add 9 and subtract 9. And then the whole goal of completing the square is that the factoring ends up being perfect squares. So this will factor into x minus, and then it's the part that's inside the parentheses before we squared it. So negative 6 divided by 2 is negative 3. So x minus 3 squared. And then afterwards I have plus 10 and minus 9, which would be a plus 1. So y equals here, and this would be the equation in standard form of my parabola. It also asks me to find the vertex, right? Once it's in this form, finding the vertex is very easy. We take the opposite of the term beside x, which would be a positive 3 here, and then we keep the second term the same. For our y value, it's a 1. So our vertex is 3, 1. All right, so the next example I'm going to do, we already have it in the standard form, so we're not going to have to work to get it there. It already looks like y equals x plus 1 quantity squared minus 9. And we're asked to find some pieces of information. And you'll notice I can fit all this on one screen because these are going to be much easier to find in this information's pattern already, or in the way that it's already presented. So your axis of symmetry is always related to this value right here, and it's the opposite of it. So it's x equals -1. Your vertex is that same x value, -1, and the y value that's at the end, the -9. Now we don't get x-intercepts and y-intercepts sort of for free in this form either. You still have to plug in, right? So y-intercept is x equals 0, and the x-intercept is y equals 0. So you do still have to do a little work on that. Our y-intercept is not too bad because if we let x equal 0, we have 0, in this case anyway, 0 plus 1 squared, which is 1, and then 1 minus 9 would give me -8. Your x-intercepts are going to be a little bit more work, so your x-intercepts is where y equals 0, so we have 0 equals, and then I have x plus 1 quantity squared minus 9. I can actually solve this one by the square root principle, again, something we did back in Chapter P. See, that Chapter P is super important stuff, guys. We're going to add the 9 to both sides, and so I'm going to have 9 equals x plus 1. I'll move all this around to give us more space in a minute. And then I can square root, and of course the square root of that's lovely, it's 3. But because I put the square root on, it's plus or minus the 3 equals the x plus 1. Okay, so thinking about it like this, basically what we're saying is that x plus 1 equals 3, or x plus 1 equals -3. And in both cases, I'll solve by subtracting a 1. So this is x equals to 2, and subtract a 1, and I've got x equals -4. So I have 2 x-intercepts. That's pretty typical. It doesn't have to be the case, but it usually is. So let me try again. Try to move this. Oh, that's not ideal. How about up here? That's a good spot for it. Okay, so our x-intercepts then are -4, 0, and 2, 0, right? Because those are x values equaling, our x values are the -4 and the 2, and the y value is 0. I didn't actually go back and write the y-intercept, my apologies, so let's do that real quick. The x is 0 and the y is -8. So that was my my y-intercept. And then these are my x-intercepts. The direction that this opens, well, the coefficient in front is a 1, right? There's an understood 1 right here, and then it's also understood to be positive in this case. So this one is going to open up. Then we're going to graph it. So let's get those pieces of information on. First, my axis of symmetry is x equals -1. So we will put that in here like this. There's my -1. The vertex is -1, -9. So it's about right here. My y-intercept is 0, -8. That would be about here. My x-intercepts are -4, 0, which would be about right there, and 2, 0 over here. Of course, it's opening upward. If you didn't have it written down at this point, you would know that it would have to just by the organization of those particular points. We'll do our best to graph it. It looks something like that. I'm sure yours looks better than mine. And we have the overall sort of image of the graph. We can also decide from here, increasing, decreasing. It doesn't ask us on this one. We could do domain and range, of course, as well. But for the increasing, decreasing, this graph is actually decreasing first, right? So it's decreasing from negative infinity to 1. I'm sorry, make that negative 1. And then it's increasing from that same negative 1 to infinity. All right, we have a couple more that I want to show you about how to get things into that standard form. I gave you one example earlier on about completing the square. As you know, completing the square is lovely on that problem. It worked out real nice and simple and easy, and it simply just doesn't always do that. So I want to show you kind of two variations of what might happen on some examples that you work on your homework for what happens when you complete the square and things aren't quite so pretty. Now, the process is, of course, the same. We're going to separate our x values from the constant values, leaving a space right here. And there'll be one right here that matches. And the key, of course, is to take negative b. I don't know why I keep saying negative, probably just because we keep working with the vertex formula. It's to take b divided by 2 and square it. We don't need to worry about positives or negatives, of course, because of the squaring. So our b value on this one is actually a negative 1. So negative 1 divided by 2 is negative 1/2, and then squared gives me actually 1/4. So we're going to add a 1/4 into our equation here. But if we add a 1/4 to compensate, we will also subtract a 1/4. Okay, so that's how that one would actually work out in terms of the choice of values to add. Again, the whole point is that this factors nicely, and by nicely I mean as a perfect square. And so it would be x minus, and it's the value that we had, or it could be plus, but it's the value that we have before we square it. So the value I had before I got 1/4 was actually a 1/2, and it was negative, so the negative is there, and it's squared. And then I have 1 minus 1/4. That's kind of like having a dollar minus a quarter. That would leave me with 3/4. And then we can identify again the vertex from this. This is my equation. The vertex would be the opposite of the value inside with x, so that would make it a positive 1/2. And then the same value is the value outside, which would make that a 3/4. So in other words, you might have to deal with fractions. Another example, if you'll take a look at this one that makes this different than the other ones, is that there is a coefficient in front of the x squared. Now, our goal is that we're going to group the x's together anyway, and so what we need to do, even if it didn't happen to be divisible evenly, is that we need this 3 to be outside. We need that term x squared on the inside of the parentheses to be a coefficient of 1. So we're going to factor that 3 out, and on this one it does work out nicely that the 12 is on the inside is also divisible by 3, so this gives me a negative 4x on the inside. I'm going to leave a space right here, just like before, and I'm going to put my plus 1 on the outside. Notice the 3 is not factored out of the plus 1 because the plus 1 is actually occurring after the parentheses occur. All right, so the key is to take the term that's b, which in this case is a negative 4, divide by 2, which gives me 2, and then squared, which gives me, again, a 4. So we're going to do plus 4 here. Now, we didn't really add 4 to the equation. We added 4 times 3, right? We really added 12. And if I added 12, I compensate by subtracting 12. That's the weirdness of this particular one, is to remember that you didn't really add 4. You really added 3 times 4, which is 12. All right, so how does this factor? Well, there's a 3 here. Factors the same way as before, right? It's x, and then it's plus or minus, whichever one we have to have, the middle term before we squared it. So this value right here is what we get, which would be negative 2. Quantity squared. And then 1 minus 12 would be negative 11 at the end. So here's my equation. And my vertex would be 2, because it's the opposite sign of the value in the middle, and negative 11. Now you might be saying, well, what about that 3? What does it do? Well, it's actually a vertical stretch, if you'll remember back to when we did transformations. Doesn't actually change how the function opens or anything like that. That 3 doesn't, but it does change that it's very narrow, and narrow, tall, thin. and instead of it being the standard ratio of a parabola. All right, we have one last thing we're talking about in this section. If you'll take a look back at the title of this section, it said inequalities in it, and we haven't done that part yet. So we're going to solve some quadratic inequalities. And this is the testing points method, or a test point method. And it works something like this. We're going to move everything onto one side. You'll have a 0 on one side, everything else on the other side. You're going to factor the non-zero side and put the numbers on a number line that you get. And then you're going to check the intervals using test points, hence the test point method name. And using those test points, you'll find the solution to the inequality. So let me show you an example of how this works. Okay, so for starters, you'll notice that the 2 is not on the same side as the rest of it. So we will move that to start with. Very simple step. This will start looking like, kind of like solving a quadratic equation. So I have x squared plus x minus 2 greater than or equal to 0. Okay. Now, we're going to attempt, if it's possible in these cases, to factor. If it does factor, yay for us. If not, we'll have to deal with it differently. This one does factor. We've got x and x. I need two numbers that multiply together to give me 2. Obviously, I don't really have any choice. It's 2 and 1. One of them is positive, the other one's negative. In this case, I have to have the 2 positive and the 1 negative in order to get the negative x in the middle here. And then what I'm going to do is I'm going to set each of these equal to 0. Yes, I do know that I'm looking for them to be greater than or equal to 0. We'll get to that in a minute. But at this point, I'm just setting them equal to 0, and I'm going to solve. So I've got x equals negative 2, and I have x equal 1. All right, so if you want to take a look, basically at this point what we've done is we've done numbers 1 and 2. Or at least 1 and part of 2. We've moved everything on the same side, and we've factored the 0, the non-zero side, and then we need to plot them on a number line. So we're going to draw a number line next. And on our number line, give yourself plenty of space, just because we're going to be doing some values here. We want to make sure, of course, we put the numbers in the right place in comparison to each other. So there's negative 2 over here, and here's a 1 over here. And what we're going to do is we're going to test points in the intervals surrounding those values. In other words, we're going to test a point before negative 2. So maybe we test negative 3. Now, if I test negative 3 and you test negative 4, it's totally not a problem. Will not hurt anything in the slightest. I need a number between negative 2 and 1. And, you know, if I can use 0 ever, I'm going to use 0 because it's an easy value to plug into stuff. So I'm going to pick a 0 here. And then I need a value bigger than 1, and so I'm going to go with 2. So these are the 3 values that I'm going to choose. So what do I do with these 3 values? Well, I need to put them into the expression that I had when I moved everything onto the same side. This one right here, the x squared plus x minus 2. So that's where I'm going to plug them in into x squared minus x, plus x, and then the minus the 2. So we're going to evaluate them one at a time. I'm going to do negative 3 first. So this is negative 3, and I'll just kind of put a colon to indicate that I'm testing negative 3. So this is negative 3 squared plus negative 3 minus 2. So this would be 9 minus 5. I'm really not concerned so much with the value, but I am in fact concerned with the sign. And this is a positive sign, right? It's a positive, in this case a 5, or a 4, but I'm getting a positive. We're going to test the next value, which was 0. Super love testing 0, super easy, right? Got lots of zeros here. And then I have minus 2, so this gives me a negative. And the last value we'll test is 2. So we'll test the number 2. We have 2 squared plus a 2 minus a 2. And again, I can worry about the actual value if you want. I mean, it's going to be 4 plus 2, which is 6 minus 2, which is 4. But I'm far more concerned really with what the value is in terms of the sign. It's a positive. So take a look back over here. I have a positive, I have a negative, and then I have a positive in terms of my number line. And the question you should be asking yourself is, why does it matter? Well, it matters because this sign said that I wanted to know what was greater than or equal to 0. Well, what does greater than or equal to 0 mean? Well, it means positive. I'm looking for the things in the parts of the graph that are positive. So that's this part and this part. And I'm going to write the interval that way. Now, notice it's actually going to include those endpoints because it said greater than or equal to 0, and we know it's equal to 0 at the endpoints. So I'm going to have brackets on here as well. So I'll have negative infinity to negative 2 bracket, union, 1 to infinity. That would be the solution set for this particular problem. One more example and we will be done. On this one, I mentioned when we started the last problem that when we could factor, we would factor, and on this one, yeah, we can't. There's no way to factor that 2 into anything but 2 and 1, and 2 and 1 will never give me the -4 in the middle. It's a highly unfortunate situation, but nevertheless it happens, right? So what are we going to do when it does? Well, what we're going to do is we're going to either do completing the square, or we're going to do the quadratic formula. And quadratic formula is what I did before, so I'll do that one again. This would be x equals, it's negative b, so that would be a +4, plus or minus b squared, which would be -4 quantity squared, minus 4a, which is 1, and c, which is 2, all over 2 times a, which is 1. So I have the 4 at the beginning, and then I have the square root of 16 minus 8, which would be 8, and then divide by 2. The square root of 8 is, of course, 2 square roots of 2 from when we were, doing that many a time before. Divide by 2. And then you have to take a look at, this is, again, some of this tripped you guys up on your very first test, that the factoring, as I divide this out, has to divide all 3 of these pieces, and of course it does. They all divide evenly by 2. So this would be 2 plus or minus the square root of 2. So again, this is 2 answers. This is 2 plus the square root of 2, and 2 minus the square root of 2. And I want to put these numbers on a number line. Well, clearly the 2 minus the square root of 2 will come first. But in order to really test the point, I probably need to have sort of an estimation in my mind of what they are equal to, so that I can choose values in and around them that make sense. So at the very least, I know this is 2 minus the square root of 2, and I have 2 plus the square root of 2. So if I grab my calculator and just get an approximation for this one, the 2 plus square root of 2 is approximately 3.4. And the 2 minus the square root of 2 is approximately 0.6. So they happen to both be positive values. So if it helps you, you can put those on there. This would be approximately 0.6. This is approximately 3.4. All right, so looking for values in and around them, between them, a nice value between them is a 1. I think I can go with a 1. I told you that I like to plug in zeros when I can, and I can plug in a 0 over here on the left-hand side. And then I need a value bigger than 3.4, so maybe we just try the number 4. And we're going to test each one of these, so that we're going to test 0 plugged in. So 0 plugged into the equation right here is what we're looking for. So I have 0 squared minus 4 times 0 plus 2. And that's a positive, right? The 2 at the end. I tried the number 1, or I was going to try the number 1 next. This is 1 squared minus 4 times 1 plus 2. So this would actually end up giving me 1 minus 4, which would be -3, plus 2, which is a negative. And last but not least, I had the number 4, and we're going to plug that one in. So this is 4 squared minus 4 times 4 plus 2. 4 squared is 16. Minus the 16 that comes next would be 0, and then I have my plus 2 to give me a positive. So I've got a positive, a negative, and a positive. And going back to the inequality where I have everything on one side, this actually tells me I want it to be less than 0, and less than 0 would be, of course, negative. So my answer is going to be the part of my number line that was negative, which happens to be the piece trapped in the middle. Now, notice that it doesn't have less than or equal to, it's just less than. So since it's just less than, we're using these parentheses, just like we were looking at in Chapter 1, to identify the region. And our answer would be the part that's trapped between that. So our solution is 2 minus the square root of 2, parenthesis, all the way up to 2 plus the square root of 2. And I would end my parenthesis.